All right. Welcome, everybody. Thank you for coming. My name is Juan, as it says on the badge. Here I'm with my friend Ary. Um, we work for a software consulting company in Argentina, and today we're going to talk about Crystal. Crystal is a programming language that we've been working on, and it's a Ruby-like language, but it is statically typed and compiled and more efficient than Ruby. And so let's see. So I want to start showing some demonstration so you can figure out what kind of applications you can run in Crystal. So let's start with a very simple example. It's a Mandelbrot set generator. So I can compile the example running Crystal build samples Mandelbrot here. So this creates an executable that I can run. So there we go. So okay. Maybe the resolution is. So we can see how much time it takes to render this. It's just 7 milliseconds. I can run, for this example, I can also run it directly using Ruby because the syntax is pretty simple, pretty similar. I mean, so if I run the same program with Ruby, we get the same result, but it takes around more than 100 milliseconds, so we get a big optimization there. So another example, it's a ray tracer. Ray tracer is a way of rendering 3D images, 3D scenes into images. So this time I'm going to compile with release mode, which adds some compile time optimizations. And I can run now, and then we get this result. This is not an image loaded from this. This is rendered on real time, and we see we got around less than 200 milliseconds, which is not bad at all. Let's see another example, which is should be much more fun. This is a Nintendo emulator written on 100% Crystal code, so I can I can load the image, and we get this is being emulated by the all running in Crystal. I'm not a big I'm not a good Mario player, but so let's get serious. So let me explain why we did this. So I said before, we work for a software consulting company. So we build software for our customers. And we often use Ruby as our primary tool. And the reason for this is Ruby fits really well into agile methodologies. It allows us to take a project from theory to practice in very quickly and maintain elegant and maintainable code. But sometimes we get some performance problems. Sometimes we have to, after some time, we need to migrate some of the backend to other languages because of performance issues. And so we normally migrate to some compiled language because compiled language tend to be faster, at least. Also, Ruby is a dynamic language, and sometimes there are some kind of errors that, if not catched by unit tests, unfortunately they are triggered at runtime. So static type checking allows us to, it contributes to catching some of those errors at compile time. And we wanted the best of each world, so we started this project to experiment with a language that can provide the flexibility of Ruby, but the advantages of a compiled and typed language. So we inherited the syntax from Ruby. This simple code here is either a Ruby or a Crystal program. Not every Ruby program is a Crystal program, and not every Crystal program is a Ruby program, as we'll see in a moment. But we inherit many of the things we like from Ruby. It's statically type checked, as I said, so we can get compile time errors about missing overloads or things like that. It generates a very efficient binary executable. We make a special emphasis on this on every aspect of the language. So I'm not a very big fan of benchmarks, but I think I can show some of the results so you can figure out where Crystal is positioned compared to other languages. So the first example is Brainfuck is interpreted of basically it's a Turing machine. As you can see, Crystal gets results very similar to the C++ implementation compared to the Ruby one, which is a very similar code base that takes like 100 times slower. The second example is matrix multiplication, and here we get even more close results to the C implementation, and Ruby is just 100 times slower. And the last example is Hablag is a benchmark set created by Google. So a member of our community ported this benchmark to Crystal, and we got a surprising result because we got even better results than the C++ implementation. And this time we compare with Python because there were no results for Ruby, probably still running. So this is a snapshot of a few days ago from GitHub of the Crystal source code. And something I want to note here, we have a growing community and a lot of people that is putting stars on our project. And for those who don't know what this means, this is like Facebook-like, right? And also notice that Crystal is written on Crystal itself, so it's complete bootstrapped by now. We've been working with this project for 3 years now. At the beginning, of course, the first implementation was not written in Crystal. The first one was written on Ruby. But once we got a stable implementation, we migrated all the code from Ruby to Crystal, and now we have a complete self-hosted. So now Ary is going to give a brief introduction of the elements of the language so you can get an idea of how to use it.
So, hi everyone, I'm Ary. So I'll give you a brief overview of the language. Of course, in 40 minutes we can say everything, but so let's begin. So let's start with the data types. Crystal is an object-oriented language, so everything's an object. And then we have two big categories. We have value, which are value types. They are allocated on the stack and are passed by value. And here we have booleans, characters. We also have the numbers. Their representation is pretty efficient. Just int32 is just 4 bytes. And then we also can define custom user types, value types, which are structs. So in this way we can create lightweight wrappers around other primitive types, so we can avoid allocating memory in most of the cases. And then the second big category is reference, which are objects that are allocated on a heap and are passed by reference. And they are managed by a garbage collector, so to free the memory for us, so we don't have to take care of memory management. And most of the objects fall in this category, right? But then Crystal introduces, has another concept, which is union types. And that happens when a variable has more than one type across different points in the program. So for example, here we have an array of mixed types, numbers and strings. And when we access one of those elements, what we get back is a union type, which is, again, a number or a string. Later we will see how to deal with these unions. Another example is when we have when we want to ask for the position of a character in a string. So the character might be there, and we return a number, that's the position. But if it's not there, we return nil, and that will mean that the character is absent, and again we have a union type. So these unions are represented in memory pretty efficiently. So here we have a union of a Boolean and a number, and they are represented with a compact struct that has a type ID, and then enough storage for all of the values that conform the union. But for some unions, we have a more efficient representation. So if you have a reference type and nil, so in our language, in some other languages, references can be nil, and this is not distinguished, but in Crystal they are different things. So string and nil are different things, and we represent this as a single pointer. If it's the null pointer, then it will be nil, and if not, it will be a pointer pointing to the data. So again, it's pretty efficient. Then, just like in Ruby, methods can accept blocks. So on the left-hand side, we have a method declaration. On the right-hand side, we have some code invoking it. And with the yield keyword on the left, what happens is that we execute the block that's passed on the right. And the right code looks really nice and really expressive. And the important thing here is that Crystal will always inline this kind of blocks. So if you write while or write it like this with a block, the generated code will be the same. There's no performance penalty at all. So you can get to be expressive, but you don't sacrifice performance. Then we also have procs, which are typed anonymous functions. So here we have a proc that receives an integer and returns an integer. In this case, you have to put the types. And these procs can also form closures, which means that they can refer to variables declared outside of the proc's body. So here we are accessing the y variable, and then we change it, and when we invoke it, the results change. Then we made a choice here that's a bit different from Ruby. In Ruby, if you want to have a method behave differently according to the number of arguments or their types, you can do this, but the way to do it is by performing runtime checks. So you ask the number of arguments or the types, and the code becomes larger and harder to understand and to read, but it's also slower because these checks are done every time you invoke the method. And in Crystal you have method overloads, so you can overload based on arity or the types. And when you invoke these methods, the compiler will infer the types of the arguments and find the matches. So if there's just one match at compile time, that call will be hard-coded to that, so there's no runtime check to be done. And if the argument types are unions and there are many matches, this decision to which overload to call will be delayed to runtime. This is usually called multiple dispatch, and it's pretty powerful. Then we, of course, based our language on Ruby, and in Ruby you don't have type annotations because it's a dynamic language, and we wanted to preserve that as much as possible. So we have a global type inference algorithm. That means types are inferred across the whole program. And for that to happen, we have to infer the types of each expression in our program. So I'll give a brief overview of this. There are some more complex details, but this is the basic idea. So let's start with the simple stuff, literals. The compiler, the language knows what their type is. So nil is nil, false and true are booleans. You have the numbers, characters, and strings. Then moving on to assignments. Here what happens is that the variable a will be bound to the type of the expression on the right-hand side. So then we have another assignment, and later we will see that the type of the nodes in our program can change over time, right? When we compile the program, And these types are transferred across the nodes. So there's really a binding between the nodes, and types travel and change. Then if we assign to a variable in multiple execution branches, different execution branches, at the end of this if, what will happen is that A will get to be a union type, right? Because in the first case we assign an integer and then a string. Now let's deal with methods and calls. So in Ruby and in Crystal too, you don't need to specify the types of the arguments. So in a way, every method is like a C++ template, if you know them. And only when you invoke them, the compiler will type it. So what will happen is that first the compiler will infer the type of the arguments. So here we have 2 integers. And the compiler will instantiate an instance of this method with those types. And then it will proceed to type the body. And in this case, it will be an integer, the result. But if we invoke this method with 2 strings, again, another instance of this method will be generated, but with 2 strings as the arguments. And then when we infer the body, we will get a string. Yes?
How does this work with separate compilation? Do you store strings?
We don't have a separate compilation. It's like in Ruby, you run the program, everything is interpreted. In our case, we have to compile everything from scratch, but it's pretty fast. Like the compiler has around 30,000 lines of code. That's excluding the standard library, and it's about 8 to 15 seconds to compile. Most of the time is taken by the code generation. The type inference is about 3-4 seconds. But we don't discard this idea of separate compilation. We have to think about it because it's these ideas are pretty, I don't know, maybe novel, and there's not a known solution for this, so we have to work it out. Continuing with methods and calls. This, of course, has to work with recursive definitions because otherwise the language is not very useful. So let's see a bit more complex example with a factorial. So again, we invoke it with a string. So an instance is generated with a string argument. And then we have an if. An if is an expression in Crystal, so it will get the value of the branch that's executed. And so its type will be the type union of the branches. So it will be, the type will be a union. And then we have the 2 branches. On one case we have a multiplication, and on the other side we have a literal. But let's start from the top, so it's the left, so it's a multiplication. And here we have factorial of an integer, and this we can deduce because n is an integer, n minus 1 is an integer. So here we need the type of fact instantiated with an integer, which is exactly the same thing that we are trying to solve. So we don't have a result for this. But what we can do is say, okay, this type will be the type of this call will be the type of this method instantiated with integer. So we bind it, and we can continue here. So we continue with the integer literal, and that's easy to type. It's an integer. So the union at least has some information that's an integer and something still unknown, but the compiler will say, okay, I have an integer, let's move it forward to fact in 32, and now we get a type, a partial type that's an integer. Now that we know that, the type is propagated to the node at the bottom, so now we know that's an integer, and we can perform the multiplication. And when we multiply 2 integers, we get an integer, and then we have the union of integer, and that's just integer. So, and that integer is again propagated up, and we are done because we don't have more types changes, like we reached a fixed point. So that's the basic idea of how it works. And there we go. So now let's consider this example. We have a string, and as I said before, we ask for the position of a character, so index asks for the position of a character in the string, And we set this because of how the method is implemented, returns an integer or nil. Now, usually in a dynamic language where all things happen in runtime, if we try to index this string with and the character was not there, we will get a runtime saying, no, you can't index a string with nil. In this case, the compiler will complain, so you won't be able to actually create a program out of this because there's no overload for this string accessor accessing a position with nil. So the compiler prevented us from making a mistake. And this also applies, for example, when you have a union type and you try to invoke a method on it. All the methods need to be in every type. So you don't get, we don't have null pointer exceptions. So basically, or invoking, you don't get undefined method at runtime. But we can solve this problem by using a check. So if we do if IDX, for those of you who know Ruby or not, the only values that can fail an if condition, so go to the else branch, are nil and false. So in the then branch of the if the condition passed, IDX can't be nil, and the compiler automatically downcasts IDX to be an integer. So it's pretty expressive, and now we can perform this operation. And another way to do it is with an isA. So this is an operator. It looks like a method, but it's part of the language. We can ask if IDX is an integer. Then inside the then branch of the if, the compiler again will downcast the variable. So we don't need a separate variable or something like that. So it's pretty comfortable to program with that. Yes?
So under the covers, is that either a null pointer or a pointer to keep allocated integer?
No, in this case, it's the first representation of a union. So you will have a small struct with a type ID, and then if it's nil, the value doesn't matter because nil is always nil, and if it's an integer, it's an integer. So it would be 8 bytes, for example, for the type ID and the integer. So we always try to take really good care for the performance. We don't do auto-boxing or stuff like that. We try to be pretty efficient. Then we have types and classes, and they can have instance variables, like in many other object-oriented languages. And the thing is here that the type of the instance variables will be inferred from the values assigned to them across the whole program. So here we instantiate a person with a name, and it's a string, so the compiler will type this name as a string. But if later in our program we create a person with an integer, the name instance variable will get the type, a union type of integer and string. And this doesn't work well with the data types. So if you have arrays or other collections, you don't want you want separate types for each collection. So we have the notion of generic types. So here we have a generic stack class with a t parameter, and we can create a stack that will only contain integers and another stack that will only contain strings. And now I'll leave you again with Juan, who will talk a bit more about concurrency and some other features.
Okay, so as we are doing a language that could perform well, we also wanted it to handle concurrency a little bit better than Ruby does. So for this topic, we inspired on other languages like Go and Erlang. These two languages have in common that they release the programmer in thinking about operating system threads and mutexes and logs and stuff like that. So in Crystal, we have this notion of lightweight processes. So you can use the spawn function that receives a block, and what it does is it will create one of these lightweight processes that we call fibers. And these fibers are managed by the language runtime, so automatically. So when you invoke spawn, it will create the fiber, and the program continues running. And the language runtime will decide when to schedule in that fiber in and out. We do always blocking I/O. So every time you invoke, for example, sending or receiving packets from the network, it will block the execution of that fiber. So at that moment, the language runtime will schedule out that fiber and schedule in another fiber that is that is waiting to be run. And when the data comes in, for example, through the network, the language runtime will schedule back in that fiber. So you don't have to deal with callbacks like in Node.js or things like that. You just write linear code, and the language runtime will figure out how to schedule the fibers. We also use this notion of channels from Go that you can use to communicate and synchronize fibers. So in this example, we create a channel that sends and receives integers, and the fiber will be awaiting for a message to come through the channel. So this is also another point where the language runtime will schedule out the fiber if the channel doesn't have messages waiting to be received. So the fiber will be scheduled out until another fiber sends a message through the channel. And this is a pretty simple concept that we can use to communicate fibers each other. It's actually inherited from another concept, which is CSP, communication sequential processes. So let's talk now about metaprogramming. Ruby is a very dynamic language. You can modify the program as it runs because the code and the data of your program lives on the same memory space. So you can change the program at runtime. But in Crystal, we cannot do that, or it would be really expensive, and we don't want that. So we needed to add another way of dealing with metaprogramming. So for example, here we have a class, and we declare two accessors of instance variables. And we see there is some duplicated code here because we declare a method with a name, and we access the instance variable with the same name. So in Ruby, you can use some special methods that come with the language that will declare those methods for us. In Crystal, we introduced the concept of macros that will execute at compile time and generate the code for us. So we can declare the getter macro, for example, and this is the simplest example of a macro that I can show. But it receives the name of the accessor that we want to generate, and you use those double bracket placeholders to replace with the nodes that we receive as arguments. So now we can rewrite our person class using this macro like this. We can also go even further and create a macro that receives many arguments, and we can iterate through those arguments and generate as many accessors as we want. So the macro system is quite powerful, and we can use it to generate and avoid a lot of boilerplate at compile time. We can even execute external processes that generate code in Crystal. And finally, as I said at the beginning, Crystal is completed bootstrapped right now. I mean, it's self-hosted. Everything is written on Crystal. So if we want to communicate with the external world, I mean, the native libraries of the operating system or the standard C library or things like that, we needed to add some way of declaring those external libraries. So, for example, we use the live block. So to declare external functions, of course, you have to annotate the type of all those functions, and then you can just invoke those functions directly in your Crystal code. We can also declare C structures and allocate them and pass pointers to the external functions. We can also use procs as function pointers to give callbacks to other libraries. And the important thing is that all this happens inside Crystal without having to go to any other language to create extensions of the language. So about the future, right now all the concurrency that I just mentioned a moment ago happens on a single thread. It's still really efficient. For example, on my machine, on this laptop, I can run a HTTP server that responds about 60,000 requests per second. But we still want to add multi-thread support so we can take advantage of all the cores of the computer. Debugger, we have only a very simple debugger, but we are working on that. Frameworks and libraries, I mean, no, yes?
No, we are only running out of time.
Oh.
Because, yeah, you gave some more time because of the delay in the start.
But
it's 30 minutes or 40 minutes right now?
It was 30, this is like 35 minutes.
Okay.
okay. Okay, well, still we're going to be hanging around, so you can come by to ask questions.
Yeah, so I think now is some time for questions.
Yes. Sure.
What do you do about GC and LLVM? I think I've seen you use LLVM as a compiler toolchain. What do you do about GC? And like, do you use GC root or do you use state point stuff?
We use, yes.
Could you please repeat the question just briefly because of the recording?
Okay. Yeah, so the question was what we use for GC, right? So we use right now we use the Bohem GC, which is an open source GC that is pluggable on native applications. We plan to replace it with something else in the future, but for the time being, it's pretty good for this purpose. Yes.
Benchmark that on C++, you use much more memory, like 3 times more memory than C++. Is it like due to garbage collection?
Probably. Also, I didn't make that benchmark, and probably the C++ implementation also takes care about the memory that it creates, and maybe the Crystal implementation is done with the with standard arrays or other structures from the standard library. So it's probably because of that.
Another question, union types, is it like available for programmer or just like compiler inherent?
So the question is if the union types are can be created by the programmer.
Can I use like union type annotations?
Yes, you can use union type annotations. For example, when you declare an overload, you can specify union, or you can create an array of union type by hand. Yes.
Can you create new value types?
Can we create new value types? Yes, absolutely. Yes, you can use instead of using class for declaring new types, you use struct, and that will generate a new value type that lives on the stack. Yes.
I think your idea of separating nil from reference type is very, very, very good. Most object-oriented languages still don't have that.
Mm-hmm.
It has been rather recently added to IFET though.
Okay. So this was just more like a comment that that Eiffel also implements nil as a separate type from reference types.
So I don't know if Ruby has operator overloading, but do you hardcode plus to always be an integer, or
Plus is a regular method. So I simplified the slides, but when you had a plus, the same process again happens for the type inference. At the bottom, we have like plus implemented for primitive types with a type.
so you can add your own type with the plus operator?
Yes, just like in Ruby.
I was wondering, you say you're not done to concurrent multi-programming yet, multi-processors yet. I was wondering if you have any restrictions on side effects and side spawns when you use access variables in this sequential persistence.
So the question was how are we planning to deal with um, shared memory between fibers, right? So this will be pretty similar to Go, in which you can share memory, but you should not. You should communicate using channels. You know, so you have to share by sending and receiving messages, and not by sharing memory. Yes.
So, in the case of Ruby, it is a slow language, but it's nice to type in, and it has, more importantly, a vast ecosystem of libraries.
Mm-hmm.
Do you find that the syntactical similarities between the two languages has helped the libraries to be ported quicker, or like, how's the ecosystem situation going on in Crystal?
So let me repeat the question. The question is if we can take advantage of the similarities between Ruby and Crystal, so Ruby libraries could be ported to Crystal. Well, it depends. For simple libraries, maybe that's true. We actually ported, the compiler itself was once written on Ruby, and we ported to Crystal very easily. That might not be true for every gem out there, but yeah, I think it should make things more easy to be ported. Yes?
And also,
Sorry.
as a quick follow-up, have you found that the syntactical similarities have garnered attention of Rubyists that have flocked to help you out with the porting efforts?
Yeah, I think so. Yeah, many members of the community that we have right now, that is pretty small, but it's growing every day. Most of them are already Ruby programmers, so, and they become interested in Crystal because of these similarities, just as we are. Okay. Okay. So still we're going to be hanging around, so if you have more questions. And by the way, we have Crystal t-shirts like this. Maybe not for everybody, but if you want one of these, you can come by and get one. So thank you. All right. Welcome, everybody. Thank you for coming. My name is Juan, as it says on the badge. Here I'm with my friend Ary. We work for a software consulting company in Argentina. And today we're going to talk about Crystal. Crystal is a programming language that we've been working on. And it's a Ruby-like language, but it is statically typed and compiled and more efficient than Ruby. And so let's see. So I want to start showing some demonstration so you can figure out what kind of applications you can run in Crystal. So let's start with a very simple example. It's a Mandelbrot set generator. So I can compile the example running Crystal build samples Mandelbrot here. So this mode, which adds some compile time optimizations. And I can run now, and then we get this result. This is not an image loaded from this. This is rendered on real time. And we see we got around less than 200 milliseconds, which is not bad at all. Let's see another example, which is should be much more fun. This is a Nintendo emulator written on 100% Crystal code. So I can I can load the image, and we get this is being emulated by the all running in Crystal. I'm not a big I'm not a good Mario player, but so let's get serious. So let me explain. Not catched by unit tests. Unfortunately, they are triggered at runtime. So static type checking allow us to it contributes to catching some of those errors at compile time. And we wanted the best of each world, so we started this project to experiment with a language that can provide the flexibility of Ruby, but the advantages of a compiled and typed language. So we inherited the syntax from Ruby. This simple code here is either a Ruby or a Crystal program. Not every Ruby program is a Crystal program, and not every Crystal program is a Ruby program, as we'll see in a moment. But we inherit many of the things we like from Ruby. It's statically type checked, as I said, so we can get compile time errors about missing over. Why we did this? So I said before, we work for a software consulting company. So we build software for our customers. And we often use Ruby as our primary tool. And the reason for this is Ruby fits really well into agile methodologies. It allows us to take a project from theory to practice in very quickly and maintain elegant and maintainable code. But sometimes we get some performance problems. Sometimes we have to, after some time, we need to migrate some of the backend to other languages because of performance issues. And so we normally migrate to some compiled language because compiled language tend to be faster, at least. Also, Ruby is a dynamic language, and sometimes there are some kind of errors that, if not, this creates an executable that I can run. So there it goes. Okay, maybe the resolution is. So we can see how much time it takes to render this. It's just 7 milliseconds. I can run, for this example, I can also run it directly using Ruby because the syntax is pretty simple, pretty similar. I mean, so if I run the same program with Ruby, we get the same result, but it takes around more than 100 milliseconds, so we get a big optimization there. So another example, it's a ray tracer. Ray tracer is a way of rendering 3D images, 3D scenes into images. So this time I'm going to compile with